Hello guys. So last time we started article chapter 4 mathematical expectation of the random variable. I gave you the difference between the random variable, I mean to say mean, and the expected value. It looks same, but they are not same because expected value that is always related with the random variable x. So mean of the random variable x, that is the expected value, I can say. And then after we went over all these things, so this is a definition that nu is equal to e of x, summation of fx, nu equal to e of x, that is for the continuous case, this is the discrete case. And then after we went over a few of the examples based on discrete and continuous case. And then after, suppose mu is not x, but it's a function of x, so g of x, so e of g of x, that's a discrete case, and this is the continuous case. If you have x over here, that means you have x here and fx. If you have gx over here, then gx and fx. Whatever you have over here, you have to multiply that part over here by fx. And then after we went over these examples, and then after, if you have two dimensions, g is a function of just not one variable x, but it's a function of two variables x and y. In that case, discrete case is this one and continuous case is this one. And finally, we went over the exercise problems, few of the exercise problems. So this one is the exercise, and we took some of the examples over here. Unfortunately, the book was closed last time, so I could not open the book. So if you want to look at the book, this is the examples. You can take the picture or you can stop the screen so that you can see this one for a long period of time. And these are the different examples. Look at over here. So article number, which is chapter 4.1, and these are the examples based on discrete and continuous case for different cases for function or random variable x, random variable gx, random variable g of x of y, all these things for discrete and continuous, both the cases. So that was all about the article 4.1. And now today we are going to start. This is the next page, another page, based on the exercise problems of article 4.1. And now, again, the same thing. And now I would like to start the next article, that is the variance and the covariance of a random variable. Variance and covariance of a random variable. First of all, what we mean by the variance. Variance means it's a kind of spreading from the mean. So this is the mean value 2, here is the mean value 2. So you can see this is the spreading from this mean value to right side as well as the left side. So this is that's called the variance. So this is suppose nu. So you can say, and you are moving like this in this and that direction, other direction, means it's x minus nu square in both the sides. Because square is there, so it is to be understood, because x square equal to 25, so x is equal to plus or minus 5, so we are moving on both the sides. So that's why it is called x minus nu square. So that's what we are going to use over here in the formula. In the second part, you can see over here, there is nu equal to 2. Another histogram, you can say, and this side and this side, that's the variance. So variance gx is always given by, look at here, look at my cursor, x minus nu square. Variance gx is equal to x minus nu square. The quantity referred to the variance of the random variable. This quantity is referred as the variance of the random variable, because we know that e of x, expected value of x, or nu of x. And now we are going to find in terms of the variance, that is the symbol of variance is sigma square, and the positive square root of sigma square, that is called, means positive square root of variance, that is the standard deviation. So how much your graph is deviate on both the sides of the mean, that can be obtained using this terminologies. So we are going to see two types of things over here. One is the variance sigma square. Second one is the standard deviation, that is a positive square root of the variance. So the variance of the random variable x, or the relative variance of a probability distribution x, that is given by sigma square equal to e of x minus nu square, e of x minus nu square. See here, square is there, because sigma square is there, and x minus nu. X minus nu, that is the variable, that is your gx function. So e of gx square, let me just share my screen so that you can come to know how these two definitions are developed, and then after we can go for this example. Let me stop this sharing this one and let me start sharing my screen. So the screen says that you know the definition of mean, that was nu of x that is equal to E of x, and that is equal to summation of x and fx over x. And same way, if I say g of x, so g of x is nothing but E of g of x, that's what we have seen in article 4.1, and that is equal to summation of g of x and fx. And here what I took my g of x that is equal to something x minus nu square. So I can write that is equal to x minus nu square. And this x minus nu square, so if I replace this g of x by x minus nu square, x minus nu square in this formula, so that is equal to summation of x minus nu square and f of x. And this is nothing but, we don't write now nu of gx or like this. You can write like this, nu of x minus nu square, but we don't write like this. That is actually same, but we write that one as the sigma square. So sigma square is equal to and this sigma square is equal to E expected value of x minus nu square, and that is equal to summation of x minus nu square of fx over the summation index x if x is discrete. X is discrete. So actually this formula is developed from the previous case, from the expected value. And same way, suppose we have sigma square is equal to E of x minus nu square, and that is equal to expected value of x minus nu square, and that is equal to negative infinity to infinity and x minus nu square and f of x and dx if x is continuous. If x is discrete and x is continuous. So these are two cases. So the quantity x minus nu over here, whatever I wrote it down, the x minus nu, or I can say this x minus nu actually. Let me write small x. Usually we write small x over here, and this is small x. So x minus nu is called the deviation of an observation from its mean. This x minus nu, that is nothing but the deviation, this x minus nu, that is nothing but the deviation of an observation, deviation of an observation, deviation of an observation from its mean, And that's why we had that histogram. This was x is equal to, or I mean, say nu is equal to 2 was there, and you have something over here, something over here, something over here. So that is called the deviation of an observation from the mean. This is your mean value. So deviation on this side and this side, deviation of an observation from the mean value. So that's how this formula is developed. And again, let me let you know this thing, that my standard deviation, that is S is equal to square root of sigma square. So positive square root of the variance, that is nothing but the standard deviation. How much your graph will deviate, how much the graph will deviate. Look at over here. So positive square root of the variance, that is the standard deviation. Okay, so that's what I wanted to let you know. And now I would like to go for my first example. Let me again stop sharing this whiteboard and let's go for the book. So book says that the first example here, that is, let the random variable x represents the number of automobiles that are used for official business purpose on any given workday. The probability distribution for company A is this one and company B is this one. Company A 123.343. Company B, x runs from 0, 1, 2, 3, 4, 0.2, 1.1, 0.3, 0.3, and 0.1. So that the variance of a probability distribution of company B is greater than the variance of company A. That means we need to find the variance. These are a discrete case because table is given. So first this formula, discrete case. So if you use nu of x, so nu of x is equal to 1 multiplied by 0.3, 2 multiplied by, because these are your x values. So x minus, so first of all, what I need to do, first of all, I need to find my x minus, I mean say my mean. my mean. So my mean nu is equal to expected value, or expected value you can say. Whenever I told you, whenever I say mean, it is to be understood that we are talking about the expected value, or mean with respect to random variable, you can say expected value. So that is given by x into fx, so 1 times 0.3, 2 times 0.4, 3 times 0.3, and that is nothing but 2. So my mean is equal to 2. Now I'm going to plug this 2 over here in the formula. So x minus 2 square and fx, and x runs from 1, 2, and 3. So x is equal to 1, 2, and 3. So if you write like this, x is equal to 1, 2, and 3, x minus 2 square, and your, this is a printing mistake over here in the book, x minus 2 square times fx. You can see over here, fx is there, so fx must be over here too. So sigma, because we are working with the company A, so just to figure it out, I would like to write sigma A square equal to summation of x minus 2 square times fx. So now x minus 2 square, and x runs from, as I told you, 1, 2, and 3. So I would like to start with 1, x replaced by 1, then plus x replaced by 2, then plus x replaced by 3, and here f of x2. X is equal to 1, 1 minus 2 equal to negative 1 square is 1, no need to write. Negative 1 square is 1, and f of 1 is equal to 0.3, so 0.3. Then after x minus 2 minus 2 is 0, no need to write. Then 3 minus 2 is equal to 1, so last part is 1, and 0.3, so 0.6. Similarly, we can refer the same thing over here for nu of b, and nu of b we are going to get, first of all, again I need to find the expected value. So I found the expected value multiplying my x and fx and summation. So I'm going to get again 2. Adding will give us 2, and then after sigma square b, now the variance is again summation of x minus nu square fx. So x minus nu square fx will be x minus nu. So x minus nu is equal to 2, x minus 2 square and fx. Replace x by 0, 1, 2, 3, and 4. Look at here, 0, 1, 2, 3, and 4. So replace this x by 0, 1, 2, 3, and 4 in between summation sign. Don't forget this square because it's the demand of the definition. And once you do like this, you're going to get 1.6. And if you compare these two, here you are going to get 0.6. Here you are going to get 1.6. That means naturally the variance over here with respect to company B, that is greater than the variance with respect to company A. And that's what that was asked to us. There is another definition of getting the variance, and that is definition. That definition is exactly same as this definition, but we can write this. We can generate the simpler form of the definition based on the first definition. So my first definition is like this, and if you open this bracket, a minus b whole square, the perfect square, x square minus 2x nu plus nu square fx, and then x square fx, and 2 nu is constant, you can pull it out of summation sign, so 2 nu and x of fx, and nu square again constant, pull it out, and summation of fx. Now you can see over here, x times fx, this part will give us, what is this? This is nothing but my nu square. Right? This is nothing but my nu square. Summation of fx is always 1 because it's a kind of probability distribution, so it is always 1. So here it is. This is my x, and fx is my mean value or expected value nu. 2 nu and nu is 2 nu square and plus nu square. So 2 nu square, negative 2 nu square plus nu square is negative of nu square. So this is negative of nu square. Look at my cursor. And x square and fx, that means here x square and fx, I mean to say that this is nothing but the expected value of x square. Look at here, x by definition, expected value of x square. So that is expected value of x square minus x square. So, but this form is quite simpler, and that's why people would usually like to go for this one whenever they want to find the variance of the given data in the discrete case. Okay, let's go for this example, and let's try to use this more advanced, or I would say general definition of variance, and try to find the variance sigma square. So I would like to go for this example. Just look at the example x and fx, and let me share my whiteboard, and let's start with this one. I would like to go for two examples over here. One is the discrete case in a tabular form, you can see over here, which I'm going to write on my whiteboard. And second one is nothing but the continuous case, 2x equal to 2 into x minus 1, x lies between 0 and 1, otherwise it is 0. And we are going to find the mean and the variance. So mean and the variance, that what we need to calculate, right? Here variance and here mean and the variance, the both the parts. So one is discrete, one is continuous case. Okay, so let me again stop sharing this book and let me start with my whiteboard. Okay, guys. So okay, so let me divide this thing into two parts. My first example says that, as I told you, we have one tabular form is given to us. X runs from 0, 1, 2, 3, 0, 1, 2, and 3, like this. And my fx value is given to us simultaneously 0.51, 0.51, 0.38, 0.10, and 0.01, 0.01. Okay, and I want to use that another definition, that is sigma square is equal to expected value of x square minus nu square. Expect x square minus nu square. So first of all, let me find my nu. Nu is nothing but expected value of x. Expected value of x is nothing but summation of x into fx over x is equal to 0, 1, 2, and 3. That means it is just multiplying of this one. So 0 times 0.51 plus 1 times 0.38 plus 2 times 0.10 plus 3 times 0.01. And if you sum this one, you are going to get that is equal to 0.61. That is equal to 0.61. And now I would like to find my EX square. So EX square, here X was there, so I just wrote it down X inside the summation sign. So naturally here I will be having x square times fx. That means I have to make the square of all my x numbers. So that is equal to 0 square, no need to write because that part is 0, and 1 square is just 1, or I can write 1 square and 0.38 plus 2 square and 0.10 plus 3 square and 0.01. And that is equal to whatever the number you are going to get, that is your EX square. Here it is 0.87. And then you can plug both of these values, this one and this one, both the values over here in the formula, you are going to get that is equal to EX square is equal to 0.87 minus nu equal to 0.61 and square. And whatever the number you are getting, that is your answer, 0.4979, 0.4979. So that is the answer, 0.0.4979. My second example, this is the example number 4.9 in the book. My second example is 4.10. Second example is 4.10. This example says that now you have one function fx is equal to 2 into x minus 1 if 0 or 1 is less than x is less than 2. Otherwise it is 0. Find the mean and the variance of x. So we need to find the mean and the variance of x. So find the mean, that means we need to find, mean means E of x, and variance means E of x square. Find the mean and the variance of x, right? Variance of x, I mean to say sigma of x square. So therefore we require E of x square because E of x square is here. Okay, so first of all, we are going to find the mean, that is E of x. So nu is equal to E of x, and E of x is equal to integration 2, because of this x, I have to write 1x over here, and x minus 1 and dx, range is equal to x is equal to 1 to 2. This 2 is constant, I can pull it out, so I can write this 2 over here, I can cancel from here. Here I'm going to get this is x square minus x. So my integration is x cubed by 3 minus x square by 2, and the range is 1 to 2. And here 2 is already out. If you replace this one, you can use the second fundamental theorem of calculus and try to figure it out, this value. So that is equal to, let me just help you out, 2, and here it is. Replace this x by the upper limit, so that is equal to 2 cube is 8, so it is 8 by 3 minus 2 square is 4 divided by 2, so that is equal to 2. In between minus sign, and now the x values are replaced by the lower limit, so that is x is equal to 1/3 minus 1 by 2, 1/3 minus 1 by 2, that is equal to, you can see over here 2 outside, and here it is 8 minus 6, because 3 is the LCM, and 8 minus 6, that is equal to 2, minus here it is the cross multiplication, 2 minus 3, that is equal to negative, negative is positive, and positive 1 by 6. Here I have 6, here I have 3, so I can divide and multiply it by 2, so that I have a common denominator. So here 2 2s are 4 plus 1, 5, so that is equal to 5, and here it is 6, and 2 is outside, so that means it is 3. So 5 by 3, that is nothing but my mean, or you can say nu. Same way you can find e of x square, and e of x square, that is equal to 2 is constant. Let me pull it out. Range of integration is, 1 to 2, and here it is x minus 1, and because of this x square, I have to multiply it by x square and dx. So that is equal to 2 times integration 1 to 2, and x square and multiplied by x minus 1, so that is x cubed minus x square and dx, and that is equal to, let me write it down over here. So that is equal to 2 times and the integration is x to the power 4 divided by 4 minus x to the power 3 divided by 3, and here it is 1 to 2. Here it is 1 to 2. Exactly same way, if you use the fundamental theorem of calculus, second fundamental theorem, you are going to get 17 by 6. Exactly same way, whatever the calculation I showed over here to you guys. And finally, I can find my sigma square equal to ex square minus nu square. So ex square, I just figured it out, that is 17 by 6, and nu, I figured it out, that was 5 by 3. Don't forget square, use your calculator, whatever the number you are going to get, that is your variance. So at this point, I would say that the variance or the standard deviation has meaning only when we compare two or more distributions that have the same units. That means when you have the variance, if you want to, just like company A and company B, so at that time you have to have the same units of the production of the companies, or items of the companies, or two companies. But suppose the units are different, in that case you cannot compare, you cannot find the variance. So please keep this thing in mind, that you have to have the same units whenever you want to compare. We shall now extend our concept of the variance of a random variable x to include the random variable, random variable related to x. Related to x means whatever I gave it to you over here, this is just my variance, right? So the variance sigma square, or you can write sigma square of x. But now I would like to consider, this is not just now x, this is not x, but I would like to consider this as some function of x, some function of x, sigma square of gx. And then after, just like our previous article 4.1, I would like to go for x and y. And that would be the end of this article. X and y means it's 2 dimensions, and that's why we are going to use the word covariance, 2 dimensions, so covariance. So that's actually mean by variance and covariance, and that justifies the title of this article, because the title is variance and the covariance for the function of random variable. Okay guys, so let me just save this file, and then after let me erase this one, and we can go for the next example or next part. So as I told you that now we are going to replace this sigma square, this x by some function of x. So x is now replaced by some function of x. Okay, so let me clear this one. I saved this one, and now let me clear the board. And let's go for the next definition. So random variables related to x. So now random variable related to the function of random variable related to x. So I mean to say that that is equal to some kind of g of x, some kind of g of x. And that's why we are going to denote that one by sigma square of g of x. This sigma square of g of x, that is equal to e of, previously it was x minus nu. Now sigma square, we didn't write anything, but at that time, as I told you, that sigma square, it was to be understood that we were dealing with sigma square of x, and that's why we were having x minus nu and whole square. But now this x is replaced by gx, so I have to have g of x minus nu whole square. Make sure that square is outside, g of x minus nu whole square, and that is equal to summation of. Now what is again the same style, whatever you have with your expected value, you have to take the same function over here multiplied by your fx. So I'm going to write that is equal to gx minus nu and square and f of x over the index of x if x is discrete. If x is discrete, this x is discrete, right? That is sigma square. And the same way, suppose I have sigma square of g of x, sigma square of g of x, and that is equal to e of g of x minus nu square, that is equal to integration g of x minus nu square and f of x and dx over the range of x if x is continuous. X is continuous. Sigma square is equal to, and that is quite simple too. So let me give you a couple examples over here. My first example based on these two definitions. This is the definition, or you can say theorem number 4.3 in your book. Okay, so my next example, that is the example number 4.11. Calculate the variance of g of x is equal to 2x plus 3, where x is the random variable of the probability with the probability distribution. X is a random variable with the probability distribution x and fx 0, 1, 2, and 3. So here it is 1/4, 1/8, 1 by 2, and 1/8. Okay, and we need to find that nu of g of x. Right, so first of all, let me find nu of g of x, because we require this new value over here. Look at here. So we require this nu. So first of all, let me find this nu. So nu is equal to nu of 2x plus 3. That is equal to expected value of 2x plus 3. And that is equal to summation of 2x plus 3 times fx. And x is equal to 0, 1, 2, and 3. So that is equal to, x is equal to 0. So it is 3 times f of 0 is 1/4. Then x is equal to 1, 2 plus 3, that is equal to 5 times, and f of 1 is equal to 1/8. Then x is equal to 2, 2 to the 4 plus 3 is 7, and it is 1 by 2. And x is equal to 3 to the 6 plus 3 is 9, and 1 by 8. And if you sum this one, you are going to get that is equal to 6. Now, I want to find the variance. So now, sigma square is equal to, or sigma square of 2x plus 3, that is my gx. So sigma square of 2x plus 3, that is equal to, okay. So, sigma square of gx, that is equal to sigma square of 2x plus 3, and that is equal to, yes please, expected value of e of, this is gx, this one gx, so that is 2x plus 3 minus nu right? Minus nu and square. 2x plus 3 minus nu and square. Already I figured it out, my nu equal to 6. So let me plug this value over here. So that is e 2x plus 3 minus 6 and square. And that is equal to expected value of 2x minus 3 and square. 2x minus 3 and square. And that can be written as expected value of 4x square minus 3 to the 6 to the 12x plus 9. That is equal to 4 out, expected value of x square minus 12 out, expected value of x plus 9 out, and expected value of 1, you can say, right? So, and 3 into, yes, 3x square, right? So sigma x square is equal to this one. Okay. So that is equal to, let me write this one after some time, but I can write like this. So that is expected value of this one is nothing but summation of, by this definition. Now, gx minus nu square is this part. So that is equal multiplied by fx. So I can write that is equal to summation of 4x square minus 12x plus 9 and my fx and x is equal to 0, 1, 2 and 3. So that is equal to x is equal to 0, 0 and 9. So 9 and here it is 1 by 4 plus x is equal to 1 square. So 4 minus 12 is negative 8 plus 1 plus 9 is 1 times 1 by 8. So 1 by 8 plus 2 square is 4, 4s are 16 and 12 2s are 24. So minus 8 plus 1 plus 9. So again it is 1 and 1 by 2 plus 3 square is 9, 4s are 36. 3 square is 9, 4s are 36 and 12 3s are 36 will get cancelled out. So we're going to get 9 and 1 by 8. And if you calculate this one, you are going to get that is equal to some value, and that is your variance. That is the variance. Same way, suppose I would like to go for one of the examples what we did, example 4.5 in the book, example 4.5 in the previous section, 4.1. So example was given to you in example 4.1, that was something like this. So let me just remove this part so that, let me erase little bit here, or I can go for the next slide. So let me save this one and I can go for the next slide. Okay. And now clear all. And I can go for the next example. This example is example 4.12. So example 4.12 says that we are going to use the example 4.5, the function given to you in the example 4.5 of article 4.1. So fx is equal to x square by 3, x square by 3, negative 1 is less than x is less than 2. And otherwise, you are going to get 0. So this example, we already figured it out, my expected value. So E of, and Gx was given to you, that is equal to 4x plus 3. So my expected value nu, that was the nu of Gx, that was E of G of x, that was E of 4x plus 3, and E of 4x plus 3, that was nothing but integration of 4x plus 3 times x square by 3 into dx, and range is negative 1 to 2. We already saw this example. You can pull this 1/3 out, and here you are going to get 4x cube plus 3x square and dx and negative 1 to 2. If you solve this one, you are going to get your new mean is equal to 1/8. Okay, and now I would like to find the variance of the same example. So now I would like to go for sigma square of gx, that is equal to sigma square of 4x plus 3, and that is equal to E of 4x plus 3 minus nu and whole square, minus nu and whole square. that is equal to expected value of 4x plus 3 minus nu is equal to 8. So that is equal to expected value of 4x minus 5 and square. That is equal to expected value of 16x square minus 20 and 40x plus 25 plus 25. So naturally, now my expected value, so by definition, I can write that is equal to integration, the same portion, 16x square minus 40x plus 25 times fx. And this fx is nothing but, x square by 3. So x square by 3 and dx, and the range of integration x is equal to -1 to 2. This can be written as, I can write this 16 out, or you can write first of all 1 by 3 out. Let me write one more step for you. And here it is 16x to the power 4 minus 40x cube plus 25x square plus 25x square, and here it is d of x. That is equal to 1/3 out, and integration 16x to the power 5 over 5 minus 40x to the power 4 over 4 plus 25x cubed divided by 3, and here x is equal to -1 to 2. Again, use the second fundamental theorem of calculus, and you're going to get this, replace x, all x's by the upper limit and then lower limit in between negative sign. X to the power 5 is 32, so 16 multiplied by 32 divided by 5 minus this 40 and 4, so here you're going to get 10 and 16, and so 160, plus here 8 multiplied by 25, that is 200 divided by 3. 200 divided by 3 minus, if you replace this x by 1, so -1 to the power 5 is negative, so -16 by 5, then negative of 10, and then -1 cube is again negative, so negative of 25 by 3. If you calculate this one, just use your simple algebra skill, and you are going to get 51 by 3. That is the answer. So that is your variance. I have not found so far the standard deviation, but you can write sigma square is equal to 51 by 3. So standard deviation S is equal to positive of square root of sigma square, that is equal to square root of 51 divided by 3. You are going to get some decimals over here, and that is your standard deviation. Okay, guys. And the last part of this article, that is now you have to be very careful, that is for covariance. That means now we are working with x and y axis simultaneously together. So let me again save this file. And let me clear this picture, and let's go for the next part. So next part is, as I told you, that it is nothing but the x and y be random variables. So definition 4.4. Definition 4.4, x and y be the random variables with the joint probability distribution x and y. So let x and y be the random variable with the joint probability distribution of function x and y. The covariance of x and y x and y is, now I'm going to define xy. Look at over here, xy, and that is equal to expected value of x minus nu x, x minus nu x, x minus nu x, and y minus nu y, y minus nu y, x minus nu x and y minus nu y, bracket complete. And that is equal to, because we have now x and y two axes, so we have to have two summation index. One is along x, second one is along y. So here it is x minus nu of x, second part is y minus nu of y, and my function f of not x but x and y, function f of x and y. This is possible when x and y both are discrete. Both are discrete. And the same way, suppose I have sigma xy equal to e of x minus nu x and y minus nu y, that is equal to integration and integration negative infinity to infinity, negative infinity to infinity, and here x minus nu of x and y minus nu of y, and f of xy, and I can write dx and dy. So this is the x with respect to x and with respect to y. Whenever we have this type of case, this is your calc 3. This is your calc 3 function of two variables. So first we are taking care of this x part, and then after this portion, and then after once we are done with this one, we can go for the outer side. Okay guys, so this is for x and y continuous. So x and y continuous, for x and y continuous. So if large values of x often result in large values of y, or small values of x results in small values of y, and positive x minus nu x will often result in positive x y minus nu y, and negative x minus nu l will often result in negative y minus nu y. So just keep this thing in mind. And now I would like to go for the covariance definition. Now again, the smaller form, I'm going to say the convenient form of the covariance definition that can also be developed using this formula. So I can write the alternating definition of the covariance, and that is given by sigma of xy, that is equal to expected value of x and y minus nu of x and nu of y. Expected value of x and y minus nu of x and nu of y. This is your theorem number 4.4 in the book. So it is also quite easy to obtain this another alternative definition using this one. That's not a big deal, but I would like to skip this one for the sake of convenience. I would like to go back to page number 96. And one function was given to you. So I would like to explain that thing to you over here. So let me write that table over here so that I don't have to change my screen again. So let me use that table here. Okay. Okay, guys. So the example 3.14, example 3.14 on page number 96 or 95 or 96, whatever it may be. This one is given okay, and it is given in this form. So let me write it down. F of xy and here it is the values of x and values of y. X is equal to 0, 1, and 2, and y is equal to 0, 1, and 2. And we are given here it is 3/28, 9/28, 3/28. Then after it is 3/14, 3/14, and 0. Then after it is given 1 over 28, then after 0, and then after 0. Whenever we have this type of things, always keep in mind this thing, guys, that here we need to write g of x, and here we are going to get h of y. Because we are going to use the marginal function on page number 116 of the book. First of all, take the sum of these three parts. If you take the sum of these three, you're going to get that is equal to 5 by 14. Sum of these two, that is equal to 6 and 9, that is equal to 15 divided by 28. Sum of this, that is equal to simply 3 over 28. Then take the sum of this one. So let me take this one. If you take the sum of from here to here, 3, 9 and 3, 6 and 9, 15. So 15 over 28. Then after, if you take the sum over here, you're going to get that is equal to 3 by 7. And here it is 1 over 28. If you add this one, if you add this 3, and if you add these 3, you must get 1 over here. This is equal to 1 or this is equal to 1. It must be matching. Okay. Now, for this example, I would like to apply this definition. I would like to find the covariance. So find the covariance. Find the covariance sigma xy. Covariance sigma xy. Okay. We already figured it out in this example 3.4 that expected value of x and y that is equal to 3 divided by 14. So we are going to use, we don't want to count the same thing again. We are going to use this part. So expected value of xy is already 3 over 14. We figured it out in our, last chapter, I think so. Example 3.14, yes, so it is chapter number 3. And then after nu of x, now I want nu of x and then nu of y. So nu of x is nothing but summation of x times g of x. That is equal to x is equal to 0 to 2 because you can see x runs from 0, 1 and 2. And that is equal to 0 times gx is equal to 3 by 14, then 1 times it is 15 by 28 plus 2 times it is 3 by 28. And that is equal to, if you count this one, you're going to get that is equal to 3 by 4. And nu of y, that is equal to summation of y into h of y. And y runs from 0, 1 and 2. 0, 1 and 2 again. So that is equal to y is equal to 0 and my h is equal to 15 by 28 plus 1 and 3 by 7 plus 2 and 1 by 28. If you count this one using the calculator, you're going to get 1 by 2. So naturally, sigma xy that is equal to expected value of xy minus nu of x and nu of y. And that is equal to, you have this value, so 3 by 4 minus 3 by 4 times 1 by 2. And if you use this one, you're going to get that is equal to 3 by, or that is equal to negative of 9 by 56. Negative of 9 by 56. So that is the variance. Now I would like to take one of the examples. This is the discrete case, right? So this is the discrete case. For discrete case. Now I would like to take one example based on the continuous case, and then after we will switch over to the examples. We will switch over to the exercise problems. So again, let me save this file and let me go for the example. It says that the fraction, example 4.14, it says that I speak for you, the fraction x of male runners and the fraction y of female runners who complete in marathon races are described by the joint density function. Whenever density word is used, always keep in mind this thing that you are working with the continuous probability distribution, so integration. And that density function density function f of xy that is equal to 8xy, 0 is less than or equal to y is less than x is less than or equal to 1, and elsewhere it is 0. Elsewhere it is 0. Find the covariance of x and y. Find the covariance of x and y. Find sigma xy, I would say. Covariance of x and y. Right? Find the covariance of x and y. Whenever you are working with function of two variables, guys, always keep in mind this thing that we have to use one definition. Let me just go back and show it to you. That is called the marginal density function. I think that is on page number. Let me just stop sharing this one and let me go for. Let me go for the book. Okay, if you go back to page number, I would say 116. Page number 116. This is the example. Look at here, guys. Page number 115 and 116. Not this one. Okay. Where is the definition? This one. Not this one. No, I'm not looking for this one. I'm looking for something else. I am not getting that definition. That definition is somewhere over here, but I just want to make sure g of xy, f of xy, x and y are continuous. Okay. Let me go back. I think that is in the previous chapter. I think it's my bad. Let me go to page number, I think 97. Okay, yes. Page number 97. You get, look at here, guys. Definition 3.2, marginal distribution. This g and y, gx and hy, these two functions, we need to separate it out from my f of xy. Please keep in mind this thing. This is your discrete case, but continuous case gx equal to f of xy and dy. Please keep in mind this thing. This is, oops. This is g of x and here it is f of x and dy. And reverse way over here, h of y, and here it is dx. So please keep in mind this thing, gx equal to negative infinity to infinity f of xy dy, hy equal to negative infinity to infinity f of xy dx. So we are going to use this marginal distribution function for our case. So again, let me go back to page number 124. Please keep in mind this thing, just take the picture because we are going to use this one a lot. Okay, so page number 124. Okay, here you can see two functions are provided to us, this gx and hy, but how can we obtain these two functions? See, that is using that marginal distribution, but we need to solve our work. So that's what we are going to do. fxy equal to 8xy and 0 to 0 is less than y is less than or equal to x is less than or equal to 1. Two dimension. So it is R2 integral. So double integration is there. Please keep in mind this thing. And first of all, we have to separate out our gx and hy because definition demands that gx and hy. For discrete case, it's not a problem because we can find gx over here on the y range and here hy on x range, and we solve this example. But please keep in mind this thing that how can we figure it out? That's the most important thing. And that's what I would like to show it to you. And finally, 4 over 225, that is the variance, covariance for this one. This function of x and y. Okay, let me again share my whiteboard. f of xy. Okay, guys. So first of all, look at here that g of x is equal to, I want to find gx, right? So g of x that is equal to, g of x is equal to integration 8xy and d of y. You know this thing. Whenever x is there, you have to have d of y over here. But your y runs from, look at here, y runs from 0 to x. Y runs from 0 to x. So y is equal to 0 to x. Y runs from 0 to x. And that is equal to, because you are integrating with respect to y, so x is constant. So 8 and x is constant. 8x, I can pull it out. And integration of y is y square by 2. And here it is, y is equal to 0 to x. That means I'm going to get 8. And so here it is 4x. And here I'm going to get x square minus y is 0. So that is equal to 4x cube. That is equal to 4x cube. So, but make sure that that is for 0 is less than or equal to x is less than or equal to 1, because now y range is already done, y is done. So now 0 is less than x is less than 1. Okay, that is for this one. Same way I can find my h of y. So h of y is equal to, now whenever you're going to find h of y, that is equal to f of xy, that is equal to 8xy. And here I have to have dx. That is the demand of the definition. Right? X and x with y and y with x. And here my range of integration must be, just look at over here. Now x lies between y to 1. So x is equal to y to 1. X is equal to y to 1. And that is equal with respect to x means this one. So 8 and y are constant. I can pull it out, and integration of x is x square by 2. And here it is y to 1, and that is equal to 8y. So naturally here it is 4y. And I'm going to get 1 square is 1 minus y square, second fundamental theorem of calculus. So I can write that is equal to 4y times 1 minus y square. 4y times 1 minus y square. So from the marginal density function we have, so therefore from this marginal density function, from these two marginal density, this is called marginal density function. Marginal density function. From these two marginal density function, we have these two marginal density function, we have nu of x that is equal to e of x, and that is equal to integration, x is there and e of x is nothing but x is there and g of x dx, right? G of x dx, and that is equal to x is there and g of x is equal to 4x cube. So 4x cube and dx, and the range of x is, you can see over here 0 to 1. So x is equal to 0 to 1. That is equal to 4x to the power 4 and dx, and x is equal to 0 to 1. That is equal to 4x to the power 5 over 5 and 0 to 1. That is equal to 4 over 5. So my nu of x that is equal to 4 over 5. Same way I can find my nu of y that is equal to e of y, and that is equal to integration of y and h of y and dy. And that is equal to integration of y and h of y is 4y into 1 minus y square and dy. 4y into 1 minus y square and dy. Once you hide this one, because once this one is done, so if you hide this one, x runs from 0 to 1. If you hide x, y runs from 0 to 1. So y is also 0 to 1, and that is equal to 4 out and integration y square minus y to the power 4 and dy, and y runs from 0 to 1, and that is equal to 4, and here it is y cube by 3 minus y to the power 5 over 5 and 0 to 1, and that is equal to 4 and 1 by 3 minus 1 by 5. So 1 by 3 minus 1 by 5, that is 5 minus, that is 2 by 15. So it is 8 by 15. So this is my nu of y. And naturally my sigma xy covariance sigma xy, that is given by exy minus nu of x and nu of y. Exy minus nu of x and nu of y. Right, guys? And that is equal to, what is my e of xy? E of xy I did not find, right? So let me just find my e of xy too. So my e of xy is also E of xy. So E of xy, that is equal to integration and xy and f of xy, that is 8xy, and that is equal to dx and dy. Range of x is equal to x lies between y to 1. So y to 1. And then after you can hide this one. So my y lies between 0 to 1. Y lies between 0 to 1. That is calc 3. So that is equal to double integration and 8x square y square and dx and dy, and x is equal to y to 1 and y is equal to 0 to 1. If you calculate this one, so first of all, try to find this part. If you find this part, you're going to get that is equal to, let me write it down over here. So that is equal to y is equal to 0 to 1 and 8y square is out because constant, and derivative integration of x square is x cubed by 3, and the range is y to 1, and here it is dy. That is equal to y is equal to 0 to 1 and 8 by 3. Let me pull it out, this 8 and this 3, and here it is y square. Inside the bracket is 1 cube is 1 minus y cube and dy. This is nothing but y minus y to the power 4. So that is equal to 8 by 3, and here it is y square by 2 minus y to the power 5 over 5 and 0 to 1. If you again use the second fundamental theorem of calculus, finally you will be getting 4 over 9. Plug these values over here. This is my 4 over 9. Nu of x, I figured it out, that is 4 over 5. Nu of y, I figured it out, that is 8 over 15. And finally, I'm going to get the answer that is equal to 4 over 225. So that is the joint covariance. Now I would like to go to a few of the examples from the exercise and then we'll stop. So let me again save this file. Let me again save this one and let me go for this one. Okay. So let's go to the book again and start with the examples. So these are the things we just went over. And now let's start the example. There are some examples I would like to consider over here. The 4.35, the random variable x, 4.35 example number 4.35. Not a big deal, simple example is there. So I would say that the random variable x representing the number of errors per 100 lines of software code has the following probability distribution x and fx using theorem blah blah blah. Find the variance of x, right? So it's quite simple, guys. Look at over here, 2 and 0.01, 3 and 0.25, 4 and 0.4, 5 and 0.3, 6 and 0.4. Values of x and fx. Okay. So let me again go back to my whiteboard so that you can come to know this thing. It's very simple. Whatever we did, exactly same thing we are going to do over here too. So exercise 4.35 for article 4.2. Okay, so it says that my nu is equal to, first of all, I need to find nu, right? And your table says that just multiply your x and fx, so 0.01 plus 3 times 0.25 plus 4 times 4 plus 5 times 0.3 plus 6 times 0.04. And if you use your calculator, you're going to get 4.11. And then after I want ex square, because you know the variance definition, sigma square is equal to e of x square minus nu square. So e of x square means I need to take the square of all this square, this square, this square, and this square. So if I take 2 square and 0.01 plus 3 square and 0.25, plus 4 square and 0.4 plus 5 square and 0.3 plus 6 square and 0.04, and whatever the number you are going to get, that is some 17.63. I just calculated this one. If you plug the values over here, so 17.63 minus 4.11, and square, and finally you will be getting 0.74. So that is the answer. So that's how you can solve the examples. That's not a big deal, very easy thing. Article 4. Example 4.43, 44, 45, and 4.33, 34, 35, 36. They all are in the same line. Let me go for example number 4.37. Example 4.37 says that is for, this is a discrete case. Discrete case. This is for continuous case. Continuous case. I have given the function fx is equal to 2 and 1 minus x, whatever we referred in our lecture. So less than 1, otherwise it is 0. Then we need to find again the covariance. Again, guys, not a big deal. We can do the same thing. We know that nu is equal to e of x, and that is equal to integration x and 2 times 1 minus x and dx. X runs from 0 to 1. 2 is constant, just pull it out. So that is equal to 2 and integration of x minus x square and dx, and 0 to 1, and that is equal to 2 and x square by 2 minus x cube by 3, and 0 to 1. So that is equal to 2 and 1 by 2 minus 1 by 3, and that is equal to 1 by 6 and 2. So 1 by 3. That is equal to 1 by 3. And naturally e of x square is equal to, again, the same part. So 2 is out, 0 to 1, and here it is x square and 1 minus x and dx. That is equal to 2 out, and this is nothing but x square minus x cube. So I can write the integration x cube by 3 minus x to the power 4 by 4 and 0 to 1. That is equal to 2, 1 by 3 minus 1 by 4. So here it is 4 minus, that is equal to 1 by 12, and here 2, so it is 1 by 6. So here it is 1 by 6. Right, guys? So once you have this one, so naturally my sigma square variance, sigma square is equal to ex square minus nu square, same definition, ex square minus nu square, that is equal to 1 by 6 minus 1 by 3 and square, that is equal to 1 by 18. 1 by 18. Example says that the dealer profit in units of $5,000 on a new automobile is a random variable x having the density function given in exercise. This function, density function, this one. Find the variance of x. Okay, now what is the profit? So the actual profit is, the actual profit is profit in variance, actual profit in variance profit. The variance is, I would say, variance is, you are getting one, you have to multiply this one, right? Sigma square, actually it is something like this. Sigma square times your $5,000. $5,000. So that is equal to 5,000 divided by sigma square is 18, and 5,000 square, sorry, because sigma square is there, right? So, and whatever the number you are getting, you have to just add that number over here. So that would be the actual profit. That would be the actual profit. Things are not difficult, guys. It's easy. Let me go through example number 4.43. That is for the, not for x, but it is for the function of x. Function of x. Let me again clear this one. And 4.43, example number 4.43, we are getting here. 4.43 says that the length of time in minutes for an airplane to obtain clearance for takeoff at a certain airport is a random variable y is equal to, now you are given the function of x. So y is equal to, you can say g of x. that is equal to y is given to you 3x minus 2. Okay, where x has the density function. Density means continuous, right? So density function is fx is equal to e to the power negative x by 4 divided by 4 if x is greater than 0, otherwise it is 0. Find the mean and the variance of the random variable y. Find the mean and the variance of the random variable. That means you need to find new y and you need to find new square of y. Find the mean and the random variance for the random variable y. Okay, sounds good. So here you can see nu of y, that is equal to expected value of 3x minus 2, and that is equal to integration of 3x minus 2 and range of integration x is equal to 0 to infinity, and here it is e to the power negative x by 4 and divided by 4 and dx. Oh, okay, and dx. You have to be careful because it's an improper integral. So I would say something like this, that limit b tends to infinity, calc 2 course, and here it is b. B tends to infinity and b. This 1 by 4th constant, let me pull it out. So limit b tends to infinity, and here it is integration x is equal to 0 to b e to the power negative x by 4 and 3x minus 2 and dx. 3x minus 2 and dx. If I write, suppose, let me change the color, maybe you will have some better idea. So I have to put how to take care of this integral. That is the good thing. Okay, so I would like to use over here the use of negative of x by 4, that is equal to u. So naturally dx is equal to negative of 4 du. Dx equal to negative 4 du. If you plug this value over here, you're going to get that is equal to 1 by 4 and limit b tends to infinity and integration x is equal to 0 to b e to the power negative x by 4. So e to the power u and 3x, x is equal to this one. So naturally my x is equal to negative of 4u. So x is equal to negative of 4u minus 2 and dx is equal to negative 4 times du. Negative 4 times du, right guys? So this is my u. Okay, that is equal to 1/4 and limit b tends to infinity, and here it is, please be careful, negative 4u square, negative positive 4u square e to the power u and du, x is equal to 0 to b plus x is equal to 0 to b e to the power u, and this is 2 and 4 is 8 times 8 and du. This is simple. This is simple because here you can take 8 out and integration e to the power u is e to the power u and x is equal to 0 to b. You can replace this u, so that is equal to 8, and here e to the power negative x by 4 and x is equal to 0 to b, and that is equal to 8 and 1 over e to the power x by 4 and x is equal to 0 to b, and this is nothing but 8, here it is 1 over e to the power b by 4 minus e to the power 0 is 1. E to the power 0 is 1, right? So actually minus 1 over here. E to the power 0 is simply 1. And now I have to pass this limit also. If I take limit as b tends to infinity, this is infinity. 1 over infinity is 0, minus 1. So this part is, this is 8. So this is simply negative of 8. So this part is negative of 8. Here I have to be a little more careful. I can take this 4 out. So here I can write that is equal to 4 out and x is equal to 0 to b. And here it is u square and e to the power u and du. U square and e to the power u and du. Okay guys, now u square e to the power u, this is u into v rule, Liet rule, L-I-A-T-E, Liet rule. Exponential function stands at last. So this is my v and this is my u, something like this. So that is equal to, don't forget 1 by 4. We are just working with this part, only this part, just like this one. So if you work with this one, so don't forget this part. So 4 times u as it is, and integration of u is u minus derivative of, I'm using product rule here. Sorry, integration by parts. So e to the power u, then after 2u and e to the power u plus 2 and e to the power u, and here x is equal to 0 to b. X is equal to 0 to b, limit b tends to infinity. That is equal to limit b tends to infinity, and here it is 4, let me pull it out, and inside the bracket, u is nothing but now e to the power, what? U is equal to, you can replace this u, or you can do something like this too, that when x is equal to 0, when both ways, when x is equal to 0, naturally u equal to 0, right? When x equal to 0, u equal to 0. When x is equal to what? X is equal to b, at that time your u is equal to negative b by 4. U equal to negative b by 4. So you can replace this range. So this is u equal to 0 to negative b by 4. So if you replace this one, so negative b by 4, that is equal to b square by 16, and e to the power u is e to the power negative b by 4, minus 2u, that is equal to negative b by 4, negative positive b by 4, and e to the power u, that is equal to negative b by 4, and plus 2 and e to the power u, that is equal to that is equal to e to the power negative b by 4. If you apply this limit b tends to infinity, 1 over b tends to infinity, that is 0, so whole part is 0, same here, whole part is 0, same here, whole part is 0, and this one, okay, 1 over b to the power 4, that is equal to this one and this one, yes, this will get cancelled out, and finally you will be getting over here some value where I was here, 3x minus 2, right? So finally I'm going to get, that is equal to, just wait guys, so nu of y is equal to, we are finding nu of y, so that is equal to some 4 times this value, so that is equal to 18, and wait, so 18 and, or I would say it is 48, right? So 48 minus 18, yes. So naturally my nu of y, that is equal to 1 by 4, don't forget this part, 1 by 4, and here it is 48 minus 8, so that is equal to 10. So that is my nu of y. Same way I can find my sigma y square is equal to now e of 3x minus 2 minus my nu square is 10 and whole square by definition. So e of 3x minus 12 and whole square. E of 3x minus 12 and whole square. And that is equal to integration 3x minus 12 and whole square, and f of xy is equal to e to the power negative x by 4 and dx 3x minus 12 and e to the power negative x by 4 and dx, and x runs from again 0 to infinity. So 0 to b and limit b tends to infinity. And just like this case, if you solve this one, you're going to get one answer. I have some answer over here. That is one, I don't know where, something 144, something like that. So that is the answer you're going to get. So make sure that which way you are taking the integration, that is more important. The way you are taking the integration, that is really, really important, because you have to have good command over the integration when you want to solve the example. So this was the example number 4.43, and I would just like to go for the last example, that is 4.45 based on the covariance, and that will be the end of today's talk. So let me save this file. And let me go for example number 4.45. Find the covariance of the random variable x and y of exercise 3.49 on page 106. Okay, exercise 3.49, page 106. So use this one, and your example number is 4.45. 4.45. Okay. So this says that we are going to use this table. Let me draw the table for you guys. This is my f of x and y. Here we are given x values 1, 2, and 3. And here I am given y values 1, 3, and 5. This is the discrete case 0.05, 0.05, 0.10, 0.05, 0.10, and 0.35, 0.00, 0.20, 0.10, and here it is, as I told you that we need to write over here gx. Here is your, this is given to us. Red pen is not given to us. This red color, we are doing this thing. If you sum this one, sum of this one, 0.1, 0.35, and 0.55. Same way, if you sum here, this, and this, you're going to get that is equal to 0.2, 0.5, and 0.3. And if you add both the ways, you must get 1. First of all, I need to find my nu of x. So nu of x, that is nothing but summation of g of x. Summation of g of x over x, so that is equal to, over x, x is equal to 1, gx is 0.1. So that is equal to 1 and 0.1 plus 2 and 0.35 plus 3 and 0.55. And if you add this one, you're going to get that is equal to something 2.45. 2.45. Same way, I need to find nu of y, that is equal to summation of y and h of y over the range of y. Y is nothing but 1, 3, and 5, and these, and these are the ranges. So here it is 1 and 0.2 plus 3 and 0.5 plus 5 and 0.3. And if you add this one, you are going to get that as some value 3.20. Okay, now I want to find E of xy. So E of xy is equal to summation and summation, and because xy, so x and y and f of x and y, and summation index, that is over y is equal to 1, 3, and 5, and x is equal to 1, 2, and 3. X is equal to 1, 2, and 3. Okay, guys, sounds good. So that is equal to f of xy. All the values are given to us. Let me first fix my value of x equal to 1. So x is equal to 1, and I'm varying my value y equal to 1, 3, 5. Same way, x is equal to 2 and y equal to 1, 3, 5. X is equal to 3, y equal to 1, 3, 5. So I'm going to write something like this. X is equal to 1 and y is equal to 1. So 1 and f of 1 and 1 plus x is equal to 1 and y is equal to 3. 1 and 3 and f of 1 and 3 plus x is equal to 1 and y is equal to 5. So f of 1 and 5. Then plus, now let me replace, the 1 is done. Now let me fix my x equal to 2. If you fix x equal to 2, again, I have to go through y equal to 1, 3, 5. So x is equal to 2 and 2 and 1. So f of 2 and 1 plus x is equal to 2, 3, f of 2 and 3. X is equal to 2, 5, f of 2 and 5. Now let me fix my 3. So if you fix 3, f of 3 and 1 plus 3 and 3, right? Y equal to 3. So f of 3 and 3 plus 3 and 5, f of 3 and 5. You can plug these values. Look at over here, guys. 1 is there, f11. 1 is here, fx1, y1, f11 is 0.05. So that is equal to 1 times 0.05 plus 3 times 1 and 3. 1 and 3, that is 0.05 again. So 0.05 plus 5 times 1 and 5 is 0 and 0. So no need to write because it is 0, 0. Then after plus 2 and 2 and 1. 2 and 1 is 0.05. So 0.05 plus 2 and 3 is 6, and here it is 2 and 3, that is equal to 0.10 plus 5 2s are 10 and 2 and 5, 2 and 5, that is equal to 0.20. So 0.20 plus, I would say that last part is 3, and f of 3 and 1, 3 and 1 is 0.10, 0.10 plus f of 3 and 3 is equal to, here it is, 3 times 3, that is equal to 9, and 3 and 3, that is equal to 0.35 plus f of 3 and 5, so 15 times f of 3 and 5, 0.10. If you use your calculator, you're going to get one number, and that is nothing but e of xy. I calculated e of xy, where is it? I don't know. That is equal to 7.85. 7.85, and finally plug the value in your formula of your covariance. Therefore, the covariance of x and y, that is equal to exy minus nu x and nu y. Exy is 7.85, nu x equal to 2.45, we figured it out, and nu y is equal to 3.20. So if you use your calculator, you're going to get the answer that is equal to 0.01. That is the answer. So that's how you can solve the examples based on variance and the standard deviation. And one small article is left out, but I think this is almost 1 hour 15, 1.5 hours. So let me stop over here. And next time we will be doing the article 4.3. Thank you guys. Let me save this file, and I will see you with our next article, that is the means and variance of a linear combination of a random variable. Linear combination means we are going to see some addition rule, subtraction rule, product rule, something like that we are going to see in the next article. Thank you so much. So let me save this one also in the folder. Clear this one, and done with this one. Stop sharing.